Hi there, this is Prof. Johan from the Department of Chemical Engineering at the University of Pretoria. Welcome to my series on the Introduction to Chemical Engineering and Chemical Engineering Principles. In today's lecture, I want to talk to you guys about hydrostatic pressure again, but specifically making reference to the hydrostatic pressure in U-tubes or manometers. Let's quickly draw a U-tube. Damn, I'm good. So here we have an open manometer. The first thing I want to mention about such an open manometer is the fact that both sides are open, which implies that the pressure working into the tube from both sides is the same, and that will be the atmospheric pressure around the system. So if I want to calculate the absolute pressure in the system, or in one of the legs of the manometer or the U-tube, I would calculate the gauge pressure and add the atmospheric pressure to that gauge pressure to get the absolute pressure in one of the legs. So I could calculate here P gauge or P absolute, depending on whether I add the atmospheric pressure to the system or not. So let's look at a closed manometer. So let's draw a closed manometer. I'm getting really good at this. I still have the atmospheric pressure, but I have a pressure inside the closed off end. There is still the pressure working into the manometer on the right hand side, or the right hand side leg of the U-tube. If P1 is now given as a gauge pressure, for me to get the absolute pressure at P1, I need to add the atmospheric pressure. And for me to get the gauge pressure anywhere in the system, I can just do my calculations. But to get the absolute pressure anywhere in the system, I need to add the atmospheric pressure again. So I can get the gauge pressure or the absolute pressure anywhere in the system again. Here we have a U-tube open on both ends. So for this system, let's assume on the left-hand side we have P1 and P2 working on the system. We have an atmospheric pressure on the outside. In this U-tube, we now have a fluid that is at this exact height. The density in the fluid we refer to as rho. So there's my fluid with density rho in this manometer, and the height on the left hand side equals the height on the right hand side, and from where the fluid level is to the bottom we call that height H, and we want to know the pressure at the point right at the bottom, and we call this pressure P. Let's talk a little bit about the U-tube or the manometer before we start doing anything else. So when we talk about pressure in a manometer or hydrostatic pressure as a whole, we always take the downwards direction as the positive H direction. So this means that H will start at the top of the system at 0 and go down and be positive, which means that the pressure here would be gauge pressure 0. And as we go down and the H increase all the way from 0 to the total length H, the pressure will increase with the rho GH equation we did last time. So this implies that the downward direction is also the direction in which the pressure increases. Now for the specific system, if we're going to talk about the pressure at the bottom of the U-tube and calculate that, we're going to start there and calculate the pressure as we go down with the equation. So P will be equals to rho GH. But my question now is this H on the left hand side or H on the right hand side? And that's actually very easy. It's both. Because both the fluids on the left and the right hand side is the same fluid with the same density, and because the left and the right hand side has got the same height, the two pressures are the same. Now that's easy to understand. What we can take from this is when we want to calculate the pressure at the bottom, it's basically a balance of what's happening down the left hand side versus what is happening down the right hand side. So we balance the pressure whether it's on the left hand side or the right hand side to the bottom. In this case it's easy to understand because we got the same fluid, they're the same heights and everything. So this is the same for the left hand side, it's the same as rho GH for the right hand side, which means that whether we start from the left or the right hand side, the pressure at the bottom P is exactly the same. Remember again, this H is actually delta H going from 0 all the way down to the bottom. So the pressure on the left hand side, the pressure on the right hand side generated by the hydrostatic force of the fluid is the same thing at the bottom, and they must be equal. So let's look at a system with two different fluids in it. So here I have a system again. Let's go and we say that we have a liquid straight to the middle and another liquid from there to the bottom. This is my first fluid with density rho 1, and this is my second fluid with density rho 2. Yet again, we want to calculate the pressure at the bottom, so we have the height in the system. On the left hand side we call this H1, on the right hand side we call this H2. And we have both systems open to the atmosphere, so we have atmospheric pressure on the outside. Let's look at this system. To calculate P at the bottom, we can go and we say that there's some sort of hydrostatic pressure generated due to the fluid column on the left, increasing as we start at the top, going down. And we can calculate that by saying P at the bottom equals density 1 multiplied by G multiplied height 1. That will give me the pressure at the bottom. But we also know that the pressure at the bottom, if we were to start on the right hand side, is equal to the density of the second fluid multiplied by the gravitational constant multiplied by the height of the second column. But when looking at this and thinking of what we said in our first example where the two fluids had the same density, we know that whatever happens on the left hand side is happening on the right hand side. These two forces should balance, and this means that the P at the bottom is the same whether I'm coming from the left hand side or whether I'm coming from the right hand side. It is still a balance, irrespective of the fact that H1 is bigger than H2. The only thing we know is that because the total product of rho GH for side 1 equals to rho GH for side 2, that as H is bigger here, we know that rho 1 should be smaller than rho 2, and that's how this system will then balance, that the product of H2 rho 2 must be equal to the product of H1 rho 1, remember G being a constant on both sides. The other thing to remember about this system is that this P we just calculated is a gauge pressure. If we want to have the P as the absolute pressure, we need to add the atmospheric pressure to have the absolute pressure at the bottom of the system. So this pressure calculated is the gauge pressure. If we want to have the absolute pressure, we must add the atmospheric pressure on both sides. So let's look at a system now where we have more than two fluids and more than one fluid in a specific leg of the U-tube or manometer. So let's say we have fluid 1, fluid 2, and then a third fluid there. There we have fluid 1, here we have fluid 2, and there we have fluid 3 with density rho 1, rho 2, and rho 3. Heights H3, call this H1, H2, and again we have the atmospheric pressure on the outside. So what is the pressure now at the bottom? But I'm also going to ask, what is the pressure there? Let's look at calculating the pressure at the bottom. By now you know that we have a balance on the left hand side and the right hand side of the U-tube. So the pressure going down this way must be equal to the pressure going down this way, and it is balanced out. So let's calculate the pressure going down the left hand leg. So we'll say that the pressure is rho 1 G H1 plus rho 2 G H2, and this is the pressure at the bottom. We also say that because it's balanced, we know that the pressure at the bottom PA will be calculated as rho 3 G H3. And again, remember, this is a gauge pressure. If we would have changed this to an absolute pressure, we would have added the atmospheric pressure on both sides. I'm going to stay with gauge pressure for my calculations for now, just to keep things simple. So there we have it. We have our balance on the left-hand side and the right-hand side getting to the pressure at the bottom. But what about the pressure at point B? Can we calculate it from the left and the right hand side? The pressure at point B will be rho 1 G H1. So we start at the top and we do the hydrostatic calculation from the top, positive H direction all the way down, and we now have the pressure at point B. Can we calculate it from the other side? And the answer is yes, we can. We must just remember one thing. This is the positive H direction, which means that is the negative H direction. So if we're going to start it at the right, we need to go all the way down past the bottom and up again to get to PB. So this means that will be equals to rho 3 GH3 minus rho 2 GH2. PA minus rho 2 GH2 will give me PB. So if I go up in the negative direction with my H, I will be able to calculate the pressure at PB. You can also see that this whole equation that we've gotten here can be obtained by rearranging the first equation for PB that we calculated. So we could have said from this equation, where we know this is true, that PB equals rho 3 GH3 minus rho 2 GH2. So yet again, this is a balance, but in this case, the balance is done like this in the YouTube. For the next system, I'm going to look at a manometer connected to a tank with a certain pressure in it. So let me draw again, and voila, there we have a U-tube or manometer connected to a tank. So we have this system open to the atmosphere. In here we have a pressure P1. P1 absolute equals P1 gauge plus P atmospheric. Remember, same as we did before with the gauge and the atmospheric pressure. So whether I refer here to the gauge or the absolute pressure is irrelevant, as long as I remember that I can convert P1 with any one of the subscripts to the other one by adding the atmospheric pressure to the gauge pressure. In our system now, we have a fluid 1 that sits with these two heights. So let's call this H1, call this H2. Density, single fluid, let's call it density 1. We can now go and say that there is still a balance in this U-tube due to pressure. What we have here is some sort of volume filled with a gas. So there we have a volume, a tank, filled with a gas, and the pressure in the gas we know is the same everywhere. So whether I'm inside the tank or down this leg of the manometer, the pressure is the same. So I can say that the pressure here is P1 as well. On the other side, I have the atmospheric pressure pushing down, and I have the head of liquid. If I want to calculate the pressure at the bottom, I know that the pressure at the bottom is now equals to, on the left-hand side of the manometer, rho 1 GH1. And on the right-hand side, I have the pressure due to this rho 2 GH2, height of fluid, but there is a pressure pushing on the top there as well. So it is plus P1. So from this, we can actually see that the pressure in the left leg equals to the pressure in the right leg. And in the right leg, we have the hydrostatic pressure due to the column of fluid, plus this P1 working on top of that fluid. So what happens if we have the same system, but with more than one fluid? So let's take this example now. In the system, let's say the first fluid starts there till there, and the second fluid sits all the way to there. So here we have fluid 1 with rho 1. We have fluid 2 with density 2. So let's call this H3, and we call this H1, we call this H2, and the pressure in this vessel, in this tank, we call that P1. So we know that rho 1 GH1 plus rho 2 GH2 equals rho 2 GH3 plus P1. So you can see there's no real difference between the examples. We just keep on balancing the one leg of the manometer to the other leg of the manometer. I can also go and calculate the pressure at this point A by saying rho 1 GH1 equals PA, and this will be equal to P1 plus rho 2 GH3 minus rho 2 GH2. And I could simplify this P1 plus rho 2 GH3 minus H2. So you can see that anywhere in the system I could actually go calculate the pressure. I could also calculate the pressure here. Let's call this B. PB equals P1 equals rho 1 GH1 plus rho 2 GH2 minus rho 2 GH3. I could simplify this as rho 2 GH2 minus H3. Okay, so as a last system, something a bit different, but not that much. For this specific system, we have a closed end on the left-hand side of the manometer now as well. And there's a pressure P2 at this end of the manometer. So nothing else has changed. I'm not going to do this example in detail. Here you can see that I've written out the total balance with P atmosphere on both sides, which means that this is the absolute pressure that I'm calculating in the system. Here you can see that we're doing a balance down the left-hand side of the manometer to a balance down the right-hand side of the manometer, same as we've done before. Thank you for watching. Until next time.